Have you ever watched a scene from Interstellar where the crew plunges into a wormhole, bending the very fabric of space and time, and wondered, could that be real? The idea of slipping through a cosmic shortcut, traversing galaxies in the blink of an eye, isn't just science fiction. It's a tantalizing possibility that physicists have been wrestling with for decades. Wormholes, those hypothetical tunnels through space-time, aren't just plot devices for blockbuster movies. They're grounded in real equations, real theories, and real dreams of unlocking the universe's greatest secrets. And today, we're diving headfirst into 30 of the most mind-bending, awe-inspiring theories about how these cosmic gateways might actually work, or why they might remain forever out of reach. Picture this, a tunnel carved into the fabric of the cosmos, connecting two distant points like a celestial subway. One moment, you're here in our solar system. The next, you're stepping out into a galaxy billions of light years away. It sounds like magic, but the math behind it is eerily plausible. Einstein's theory of general relativity suggests that space-time can warp, bend, and even fold, creating bridges we call wormholes. But here's the catch. These cosmic shortcuts aren't just sitting around waiting for us to stroll through. They're shrouded in mystery, tangled with paradoxes, and guarded by laws of physics that might make them impossible to traverse. Or might not. So what's really out there? Could wormholes be the key to interstellar travel, or are they cosmic dead ends? Are they natural phenomena waiting to be discovered, or would we need to build them ourselves? And what about the dangers? Would crossing one rip you apart, send you hurtling through time, or something even stranger? Over the next 30 theories, we'll explore the wild, the plausible, and the downright terrifying ideas that scientists have proposed. From black hole connections to quantum entanglement, from time loops to civilizations harnessing wormholes as highways, this isn't just about understanding the universe. It's about daring to imagine our place within it. So buckle up. We're about to take a journey through the most thrilling frontiers of physics, where the line between science and science fiction blurs. And the cosmos has never felt so close. Einstein and Rosen didn't set out to discover cosmic shortcuts. They were simply probing the deepest implications of general relativity when they stumbled upon something extraordinary. Back in 1935, their calculations revealed that black holes might not be just bottomless pits in space, but potential doorways. They pictured spacetime stretched thin like a rubber sheet, pinched together until two distant regions touched, forming a tunnel, a theoretical passage between them. These bridges didn't just connect space, they warped time itself, threading the needle between the universe's distant corners in a way that defied conventional travel. But here's the twist, these bridges weren't exactly welcoming. The equations suggested that passing through one would be like stepping into a cosmic shredder. The throat of the wormhole would snap shut faster than light could cross it, crushed by its own gravity. It was a tantalizing idea, proof that spacetime could stitch itself into tunnels, but a practical dead end. Einstein himself saw it more as a mathematical quirk than a blueprint for interstellar travel. Yet buried in those calculations was a revelation. The universe might be threaded with hidden connections woven into the fabric of reality itself. For decades, physicists dismissed these bridges as beautiful but useless until new theories breathed life into them. Imagine spacetime not as a static backdrop but as a living, twisting entity. Quantum physics hinted that exotic matter with negative energy could prop a wormhole open, defying gravity's deadly grip. Suddenly, Einstein and Rosen's curiosity became a frontier. Their bridge wasn't just a relic of math, it was a challenge. Could we stabilize it? Could we traverse it? Or was it always meant to be a cosmic riddle, taunting us with possibilities just out of reach? Einstein and Rosen's bridges might have seemed like cosmic dead ends, but in 1988, physicists Michael Morris and Kip Thorne dared to ask, what if we could prop them open? Their work sparked a revolution, transforming wormholes from mathematical curiosities into potential highways across the universe. The key, something called exotic matter, a hypothetical substance with negative energy, bending the rules of physics as we know it. Picture this: normal matter, like the stuff around us, creates gravity that pulls things together. But exotic matter would do the opposite, generating a kind of anti-gravity that could counteract a wormhole's natural tendency to collapse. Morris and Thorne calculated that lining a wormhole's throat with this strange material might just keep it stable long enough for someone or something to pass through. But here's where things get tricky. Exotic matter isn't just rare, it might not exist at all. The closest we've come is the Casimir effect, a bizarre quantum phenomenon where empty space itself can produce negative energy under specific conditions. But the amounts needed to stabilize a wormhole, they dwarf anything we've ever observed, and even if we could scrape together enough, the challenges don't stop there. A traversable wormhole would need to be enormous. Think planet size to prevent tidal forces from stretching you into a human noodle. The gravitational pull at its edges would need to be gentle enough to avoid spaghettification, that gruesome fate awaiting anyone who gets too close to a black hole's edge. Then there's the question of control. A wormhole isn't just a door, it's a dynamic structure sensitive to every particle passing through. Even a single photon could destabilize it, triggering a catastrophic collapse. Some theories suggest advanced civilizations might use force fields or additional layers of exotic matter to shield their wormholes, like reinforcing a tunnel with cosmic steel beams. But for now, these are just thought experiments pushing the boundaries of what physics allows. Morris and Thorne's work didn't just reopen Einstein's old bridges, it gave us a blueprint to dream bigger. The universe might still forbid shortcuts, but for the first time we're asking how instead of if, and that changes everything. What if a wormhole didn't just connect 2 points in space but 2 moments in time? The idea of twisting these cosmic tunnels into time machines isn't just the stuff of novels like Carl Sagan's Contact, where a wormhole becomes humanity's gateway to the stars and beyond. It's a chilling possibility embedded in Einstein's equations. Picture one end of a wormhole anchored near Earth while the other hurtles away at near light speed. Thanks to time dilation, where motion slows time for the traveling end, returning through the tunnel could drop you into your own past. The result, a closed time-like curve, a loop in spacetime where cause and effect start to tangle in unsettling ways. But here's where physics gets messy. Step into one of these loops and you might face the infamous grandfather paradox. Kill your ancestor before your parent is born, and suddenly you could never exist to commit the act in the first place. The universe seems to recoil at such contradictions. Stephen Hawking even proposed the chronology protection conjecture, a cosmic rule that might prevent time travel outright. He argued that quantum effects, like a flood of infinite energy bursting from the vacuum of space, would destroy any wormhole-turned time machine before it could be used. Nature, it seems, abhors a time traveler, yet some theorists aren't ready to give up. They speculate that alternate timelines or self-correcting events could resolve these paradoxes. In one scenario, the universe might twist itself into knots to ensure consistency. Your actions in the past were always part of history, even if you didn't know it. Or perhaps every choice spawns a new reality, sidestepping paradoxes entirely. Wormholes as time machines stretch our understanding of reality to the breaking point, forcing us to ask, is time a rigid thread or a tangled web waiting to be rewoven? Sagan's fictional explorers found wonder in their cosmic shortcut, but the real universe might guard its secrets more fiercely, locking time's door with laws we're only beginning to decode. At the smallest scales imaginable, where spacetime itself becomes frothy and unpredictable, lies a realm where wormholes might flicker in and out of existence like quantum fireflies. This is the Planck scale, a dizzying domain where distances shrink to a trillionth of the width of an atom, and the very fabric of reality trembles with uncertainty. Here, according to some theories, space-time isn't smooth and continuous. Instead, it's a seething quantum foam, bubbling with tiny, fleeting wormholes that form and vanish in fractions of a second. These aren't the cosmic tunnels of sci-fi dreams. They're ghostly strands woven into the quantum underworld, far too small and short-lived for even the most advanced microscopes to catch. But why would nature bother with such ephemeral structures? For physicists wrestling with the marriage of quantum mechanics and gravity, these microscopic wormholes might hold the keys to a grand unification. Einstein's general relativity describes gravity as the curvature of spacetime, while quantum mechanics governs the frenetic dance of particles. Yet the two theories refuse to play nice, especially in extreme environments like black holes or the Big Bang. Quantum wormholes could be part of the glue that binds them, offering a bridge between the vast and the vanishingly small. Some models suggest these fleeting tunnels might even stitch together separate universes in a vast multiverse, like threads connecting patches of a cosmic quilt. The catch: their existence is almost poetic in its elusiveness. A Planck-scale wormhole would live for roughly 10 to the power of -43 seconds, the shortest meaningful interval in physics. By the time you blinked, trillions of them could have flared into being and vanished. Detecting something so tiny and transient would require technology far beyond our wildest dreams, perhaps harnessing energies comparable to the birth of the universe itself. Even then, their effects might be so subtle they'd blend into the quantum noise like whispers lost in a hurricane, yet their theoretical implications are colossal. If spacetime is indeed foamy at this scale, it could rewrite our understanding of vacuum energy, dark matter, or even the speed of light's constancy. Some researchers speculate that entangled particles, those spooky twins of quantum physics, might be linked by microscopic wormholes, offering a tangible mechanism for their instant connection across vast distances. Others wonder if black holes, those cosmic vacuum cleaners, might spit information back out through these quantum backdoors, solving the infamous information paradox. For now, these ideas lie at the edge of theory, where mathematics dances with imagination. The quantum foam's wormholes remain as elusive as shadows in a dark room, but if they're real, they're proof that the universe's smallest corners might hide its biggest surprises. The heart of a black hole has long been described as a singularity, a point of infinite density where spacetime curves to its breaking point and the laws of physics simply give up. But what if that terrifying void isn't an endpoint at all? Some theories propose that hidden within the crushing depths of a black hole's core might lie a wormhole, a secret passage leading not to oblivion but to another corner of the universe, or even another universe entirely. This radical idea turns the traditional view of black holes upside down, suggesting that these cosmic monsters might not be dead ends but gateways to something far stranger. Take the classic image of a black hole, an event horizon, the point of no return where gravity's grip becomes unstoppable. Beyond that boundary, matter is thought to spiral inward, crushed into the singularity. But what if, just beyond that horizon, spacetime folds inward like a cosmic origami, twisting into a tunnel instead of a dead stop? The mathematics of general relativity actually allows for this possibility. A black hole's singularity could theoretically unfold into a white hole, spewing out matter and energy somewhere else in the cosmos. Picture a black hole in our galaxy connected to a white hole in a distant galaxy, forming a wormhole bridge between them. Matter falls in here, erupts out there, a one-way trip through the universe's plumbing. But there's a problem with this elegant idea, the dreaded firewall paradox. Quantum physics suggests that the event horizon of a black hole might not be the smooth, invisible barrier relativity predicts. Instead, it could be a searing wall of energy, a firewall that would instantly vaporize anything trying to pass through. If that's true, then any wormhole lurking inside would be cut off, rendered useless by a curtain of destruction. Recent research has scrambled to reconcile these two views. Some physicists argue that firewalls might not form under certain conditions, leaving the door open, literally, for wormholes to exist. Others propose that black holes could transition into wormholes under extreme conditions, like spinning at near light speed or merging with another black hole, warping spacetime so violently that a tunnel forms in the chaos. The implications are staggering. If even one black hole in the universe hides a traversable wormhole, it could rewrite our understanding of cosmic travel. Imagine civilizations far more advanced than ours using these natural shortcuts to hop between galaxies. Or consider the terrifying alternative: a wormhole could collapse unpredictably, snapping shut mid-journey and scattering its contents across time and space. The universe might be littered with these half-formed passageways, some stable, others lethal. For now, the truth remains locked behind the event horizon's veil, where the line between a death trap and a doorway blurs into quantum uncertainty. If black holes are the universe's insatiable vacuum cleaners, sucking in matter with relentless gravity, then white holes would be their polar opposites, cosmic fountains, violently spewing out energy and matter in a torrent that nothing can enter. The equations of general relativity allow for these bizarre objects, painting them as the theoretical exits of wormholes, the bright counterpoints to their dark counterparts. Picture a black hole's singularity as a tunnel's entrance, twisting spacetime until it reconnects somewhere else, where a white hole explosively ejects everything that fell in. It's a one-way trip through the cosmos plumbing, a grand cosmic recycling system hidden in plain sight. Yet for all their mathematical elegance, white holes suffer from a glaring problem: we've never seen one. The universe seems obsessed with creating black holes, collapsing stars, galactic cores, even microscopic ones in particle accelerators, but white holes remain stubbornly absent. Why? The answer might lie in their inherent instability. A white hole, by definition, refuses to let anything in, only out. That means any stray particle or dust grain drifting too close would disrupt its delicate balance, triggering a collapse into a black hole. In other words, white holes might be cosmic mayflies, flaring into existence for mere moments before vanishing forever. That hasn't stopped theorists from hunting for their fingerprints. Some speculate that gamma-ray bursts, those brilliant flashes of energy visible across the universe, could be the dying screams of white holes. These explosions, some of the most energetic events since the Big Bang, might mark the moment a white hole's fragile structure fails, unleashing pent-up energy in a final, catastrophic burst. Others suggest that certain anomalies in cosmic microwave background radiation, the faint afterglow of the universe's birth, could reveal ancient white holes flickering in the early cosmos, long before matter and gravity stabilized into the universe we know. Even stranger is the idea that white holes might not just be relics of the past, but active players in a cyclical cosmos. If our universe emerged from the collapse of a previous one, a concept known as the Big Bounce, then the Big Bang itself could have been a white hole event, vomiting out space-time and matter from a parent universe's demise. Wormholes threading through this process might connect entire cosmic epochs, stitching together realities like pages in an infinite book. For now, these ideas live at the edge of theory, where mathematics dances with imagination. White holes taunt us with their possibility, whispering that the universe's exits might be as mysterious as its entrances, and just waiting to be found. String theory rewrites the rules of reality by proposing that the universe isn't just three-dimensional, it's a symphony of hidden dimensions, curled up so tightly we've never noticed them. And if these extra dimensions exist, they might be the missing ingredient for stable wormholes. Picture our universe as a three-dimensional brain, floating in a higher dimensional space, like a sheet of paper suspended in a vast cosmic ocean. Lisa Randall's groundbreaking work on warped geometries suggests that gravity, unlike other forces, could leak into these extra dimensions, bending spacetime in ways that create shortcuts between distant points. A wormhole in this scenario wouldn't just tunnel through our familiar dimensions. It could dip into the hyperspace beyond, slicing across the cosmic bulk like a knife through folded layers of fabric. The math gets dizzying fast. In Randall's warped brain model, two distant regions of our universe could be millimeters apart in a fifth dimension, just like 2 points on opposite ends of a folded napkin might touch when pressed together. A wormhole threading through that higher dimensional gap could bypass light years of conventional space, turning a journey across the galaxy into a stroll through a hyperdimensional backdoor. But here's the catch: traversing such a wormhole would require technologies capable of manipulating dimensions themselves. Imagine a civilization that could pinch space-time not just left or right, but outward into unseen directions, stitching together portals like a seamstress working in 4D. Yet string theory's wormholes come with their own paradoxes. Some models suggest these tunnels would be riddled with quantum instabilities, collapsing the moment anything tried to pass through. Others propose that higher dimensional physics might naturally stabilize them, with exotic strings, the theory's fundamental vibrating threads acting as cosmic reinforcement beams. The most tantalizing idea, that wormholes could be the universe's original umbilical cords, remnants of the Big Bang when brains collided and higher dimensional bridges briefly formed. If true, the cosmos might be webbed with ancient, invisible tunnels, their endpoints hidden in plain sight, waiting for a physics-savvy species to unravel their secrets. Randall's work doesn't just offer a new blueprint for wormholes, it forces us to rethink the very fabric of connectivity. If extra dimensions are real, then the universe's most dramatic shortcuts might not be holes punched through space, but detours through the dimensions we've yet to see. The irony is exquisite. To find the tunnels that bridge our world, we might first need to step outside of it entirely. Long before galaxies or stars ignited, the newborn universe might have been threaded with cosmic strings, space-time floors so dense a single inch could outweigh Mount Everest. These hypothetical relics of the Big Bang aren't just ultra-dense oddities. They could be the universe's original wormhole weavers. Imagine space-time as a frozen lake cracking under pressure, forming fissures that stretch across the cosmos. Cosmic strings would be those cracks, infinitely thin, yet warping gravity so intensely they could bend light into rings or slice through space itself. And if two strings crossed or tangled, the math suggests space-time might twist into a knot so tight it punctures, forming a wormhole linking distant regions like stitches in cosmic fabric. Unlike black hole wormholes, which crush anything that enters, string-borne tunnels could be strangely clean. With no event horizons or singularities, they might act as pure gravitational shortcuts, no exotic matter required. Their sheer mass would bend space-time into a tunnel naturally, like a bowling ball sinking into a trampoline. Astronomers have even hunted for their fingerprints, bizarre gravitational lenses where distant galaxies appear mirrored or stretched into perfect arcs. A cosmic string drifting between us and a star could split its light like a prism, creating twin images perfectly aligned. While no confirmed detection exists, these eerie symmetries in deep-field telescope images keep theorists watching the skies. But the wildest possibility, cosmic strings might not just connect space, they could bridge time. If a string loops at near light speed, its insane gravity could warp time around it so severely that passing through might send you backward. Picture a string the length of a galaxy, vibrating like a plucked guitar string. The oscillations could create time-delayed echoes in the cosmic microwave background, whispers of the universe's first moments encoded in ancient light. Some models even suggest colliding strings might spawn closed time-like curves, those paradoxical loops where cause and effect crumble. Yet for all their potential, cosmic strings suffer from a cosmic irony. The finer we comb the universe, the less evidence we find. Inflationary theory, the leading model of the Big Bang, predicts strings should be everywhere, yet the cosmos seems suspiciously smooth. Are they hiding in plain sight, masquerading as dark matter filaments? Or did they snap like overstretched rubber bands long ago, leaving only wormholes as their ghosts, until we spot a telltale lens or a ripple in spacetime's fabric? These primordial defects remain both a tantalizing wormhole factory and a cosmic what if, reminding us that the universe's boldest architects might have been its earliest. Dark energy, the invisible force stretching our universe apart at an ever-increasing rate, might hold the key to wormholes' greatest secrets or their eventual demise. Imagine spacetime as an inflating balloon, galaxies painted on its surface drifting farther apart as some mysterious pressure fills the interior. Now picture a wormhole threading through that balloon, a tunnel trying to stay open while the fabric around it billows outward relentlessly. This cosmic tug of war between dark energy's repulsive push and the wormhole's gravitational pull could rewrite the rules of interstellar travel. One radical theory suggests wormholes might not just resist dark energy, they could feed on it. Like drains in the cosmic bathtub, these tunnels might siphon off dark energy to stabilize their own structure. The math reveals a stunning possibility. As space expands elsewhere, the wormhole's throat could contract just enough to balance the forces, using the universe's acceleration against itself. Advanced civilizations might even exploit this, positioning wormholes near dark energy hotspots to harvest its repulsive power. Think of it as cosmic engineering on a galactic scale, turning the vacuum of space itself into fuel for immortality. But there's a darker scenario. If dark energy's strength increases over time, a possibility called the Big Rip, it could tear wormholes apart from the inside out. The same force that keeps the tunnel open today might stretch it too thin tomorrow, like taffy pulled until it snaps. Some models predict wormholes in a high dark energy universe would evaporate in flashes of Hawking radiation, their final moments echoing across spacetime like dying stars. Others speculate that surviving tunnels could become time capsules, preserving pockets of pre-expansion physics in their cores, like amber trapping ancient insects. The strangest twist, dark energy might not just affect wormholes, it could be them. Quantum field theory hints that what we perceive as dark energy could actually be the collective gravitational influence of countless microscopic wormholes woven through the vacuum. Every cubic inch of empty space might thrum with these unseen tunnels, their combined push driving the universe's acceleration. It's a dizzying thought. The force tearing galaxies apart could be the breath of wormholes too small to see, breathing in unison across the cosmos. Yet for all these possibilities, dark energy remains shadowy 95% of the universe's energy budget, yet detectable only by its fingerprints on expanding space. Future telescopes mapping the universe's large-scale structure might spot anomalies, regions where expansion slows inexplicably, hinting at hidden wormhole networks siphoning off energy. Or perhaps the James Webb Space Telescope will catch distant quasars flickering in unison, their light bent by invisible tunnels warping spacetime between them. Until then, this dance between cosmic shortcuts and cosmic expansion remains one of physics' most tantalizing puzzles, where the universe's greatest mystery might be the very thing that makes its shortcuts possible. What if every wormhole is actually a cosmic mirage, a shadow cast by something far stranger happening at the universe's edges? The holographic principle turns our intuition about reality inside out, suggesting that all the information in a three-dimensional space might actually be encoded on a two-dimensional surface, like a movie projected from the walls of the cosmos. And if that's true, wormholes could be the glue stitching this hologram together, tying distant points together not through traditional tunnels but through quantum entanglement itself. Enter the ER=EPR conjecture, a bombshell idea from physicists Juan Maldacena and Leonard Susskind. At first glance, it seems almost poetic in its simplicity. Einstein-Rosen bridges, those same wormholes Einstein toyed with in the 1930s, might be indistinguishable from entangled particles, the spooky action at a distance that baffled Einstein himself. Picture two electrons born from the same quantum event, forever linked so that changing one instantly affects the other, no matter how far apart they drift. Now imagine that connection isn't just a mathematical quirk, but a physical bridge, a microscopic wormhole threading through the fabric of space-time. The implications are staggering. If every pair of entangled particles is secretly joined by a Planck-scale wormhole, then the universe might be webbed with invisible tunnels, their combined structure upholding reality like invisible scaffolding. This isn't just philosophy, it's grounded in the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT, a groundbreaking framework where a wormhole in a higher dimensional bulk space corresponds to entangled quantum states on its lower dimensional boundary. Think of it like a cosmic vending machine. Drop in a quantum equation describing entangled particles, the EPR side, and out pops a geometric description of a wormhole, the ER side. The math doesn't just suggest they're related, it screams they're two faces of the same coin. But here's where it gets surreal. If ER equals EPR holds, then building a traversable wormhole might not require exotic matter or cosmic strings, just perfect control over quantum entanglement. A civilization advanced enough to entangle macroscopic objects could theoretically pull on those quantum threads hard enough to stretch space-time into a tunnel, like knitting a sweater from the fabric of reality itself. Suddenly, wormholes stop being just astronomical curiosities and start looking like the ultimate quantum technology, waiting for a species clever enough to harness them. Yet the holographic view also raises thorny questions. If wormholes are entanglement made tangible, does that mean every time we create entangled particles in a lab, we're unknowingly spawning microscopic wormholes? And what happens to these tunnels when we measure one particle collapsing its quantum state? Does the wormhole snap shut, or does it linger like a ghostly afterimage? The holographic principle doesn't just redefine wormholes, it blurs the line between information and infrastructure, suggesting that the universe's deepest connections might not be made of matter or energy, but of pure woven data. For now, ER equals EPR remains a dazzling hypothesis, a bridge between quantum mechanics and gravity that even its creators admit is more metaphor than proven fact. But if it's right, then the universe's greatest shortcuts might not be tunnels through space but handshakes between particles, whispering across dimensions we're only beginning to map. If string theory paints the universe with extra dimensions and vibrating strings, loop quantum gravity takes a wildly different approach, imagining spacetime not as smooth fabric, but as a tapestry of tiny, indivisible threads. This radical framework suggests that at the Planck scale, reality isn't continuous. Instead, it's woven from discrete loops like pixels forming the cosmic screen we call spacetime. And in this pixelated landscape, wormholes might emerge not as tunnels carved through space, but as quantum stitches where those threads knot and reconnect in unexpected ways. Recent simulations in loop quantum cosmology, a cousin of the full theory, have given us tantalizing glimpses of how this might work. When physicists modeled the birth of a universe in this framework, they found something astonishing. As quantum fluctuations twisted spacetime's threads, microscopic wormholes flickered into existence like glitches in reality's code. Unlike string theory's higher dimensional bridges, these tunnels didn't require exotic matter or cosmic strings. They were natural byproducts of spacetime's graininess, forming where loops tangled tightly enough to puncture the fabric between 2 points. Picture a knitted sweater snagging so hard that 2 distant stitches get pulled together, a flaw that becomes a shortcut. The contrast with string theory couldn't be sharper. Where string theory's wormholes demand hidden dimensions and delicate balances of energy, loop quantum gravity offers tunnels that are almost inevitable. Here, wormholes aren't cosmic luxuries, they're quantum inevitabilities bubbling up from spacetime's fundamental structure. Some models even suggest that black holes could transform into wormholes as their singularities quantum bounce, avoiding infinite density by rebounding into new spacetime nodes. It's a universe where death and rebirth are written into the code, where every collapse might seed a new passage. Yet challenges remain. These simulations are still in their infancy, and scaling up from quantum wormholes to traversable tunnels would require spacetime's threads to knot in just the right way. Too loose and the passage collapses. Too tight and tidal forces would shred anything attempting the crossing. Some physicists speculate that advanced civilizations might one day manipulate these quantum threads directly, weaving wormholes like cosmic spiders spinning silk. Others caution that the universe's underlying code might have built-in firewalls, protocols that prevent spacetime from being hacked too easily. What's breathtaking is how loop quantum gravity reframes the very idea of a shortcut. Wormholes here aren't anomalies, they're part of spacetime's original design, waiting to be decoded. While string theory's tunnels feel like engineering projects, structures to be built, loop quantum gravity whispers that they might have been here all along, stitched into reality's seams, just waiting for us to notice. If our universe is just one bubble in an endless cosmic foam, then wormholes might be the threads stitching that vast tapestry together. The multiverse theory, particularly Max Tegmark's level Roman III interpretation, suggests that every quantum decision spawns a new reality, branching endlessly like a fractal tree. In this view, wormholes could act as bridges between these parallel worlds, tunnels not just through space but across realities themselves. Picture stepping into a wormhole here and emerging in a universe where gravity is twice as strong, light travels slower, or history unfolded without the dinosaurs' extinction. These wouldn't just be distant galaxies, they'd be alien cosmoses with fundamentally different rules. Tegmark's framework classifies the multiverse into 4 levels, with level Roman III focusing on quantum branching, the idea that every possible outcome of every quantum event creates a new timeline. Wormholes threading through this labyrinth could connect versions of you living alternate lives, each shaped by different choices. The mathematics even allows for these tunnels to remain stable if they're anchored to cosmic constants that transcend individual universes, like the underlying quantum fields that birth particles. Imagine a civilization that learns to map these tunnels, not just to explore space, but to surf the waves of probability itself. But the real shocker: some of these bubble universes might be closer than we think. String theory's landscape of possible vacuum states suggests that another universe with different physical constants could be hovering millimeters away in a hidden dimension, separated only by an energy barrier too high to cross unless a wormhole punched through. If that's true, these cosmic backdoors wouldn't just lead to faraway places, but to realities coexisting alongside ours like ghostly reflections. The catch: navigating such a wormhole would be like playing Russian roulette with physics. A tunnel might deposit you in a universe where electromagnetism is too weak for atoms to form, or where dark energy rips spacetime apart instantly. Even if you found a stable passage, returning home could be impossible. Your original universe might lie forever out of reach, its quantum signature shifting the moment you left. Some theorists argue this isn't a bug but a feature, the multiverse's ultimate firewall, ensuring no reality contaminates another. Yet the wildest implication isn't travel, it's communication. If entangled particles share invisible wormholes within our universe, could particles in parallel worlds be similarly linked? A lab in Universe A might send data through a quantum wormhole to Universe B, bypassing light speed limits entirely. The messages would be cryptic shadows of probabilities flickering between realities, but proof that we're not alone in the cosmic foam. Tegmark's vision doesn't just expand the universe, it transforms it into a hall of mirrors where every reflection is a door waiting to be opened, or a warning whispering, "Step through at your own risk." The Big Bang wasn't just an explosion, it was a cosmic crucible, forging space-time in a frenzy of expansion so violent that the very fabric of reality might have torn. And in those first searing moments, as the universe inflated faster than light itself, nature could have stitched wormholes into existence like scars on newborn space-time. These wouldn't be the delicate tunnels of later eras propped open by exotic matter or quantum tricks. These would be primordial beasts forged in the furnace of creation, their throats wide enough to swallow galaxies whole, or perhaps frozen shut by the universe's cooling breath, left lurking in the cosmic shadows as relics of a hotter, wilder time. Clues to their existence might be hiding in plain sight, etched into the afterglow of the Big Bang itself. The cosmic microwave background, that faint whisper of radiation from the universe's infancy, should be nearly uniform, a smooth tapestry of microwaves stretched across the sky. But look closer and odd wrinkles appear, cold spots where the temperature dips unexpectedly, hot streaks where energy clumps in ways standard physics struggles to explain. Some theorists argue these anomalies could be the fingerprints of ancient wormholes, their gravitational shadows warping the early universe's light like fingers pressing into wet clay. Picture a wormhole's mouth distorting the plasma of the young cosmos, leaving a telltale swirl in the radiation that would freeze into the CMB's patterns as the universe expanded. Yet if these tunnels are out there, why haven't we stumbled over one? The answer might lie in their gargantuan scale, or their microscopic one. Inflation-era wormholes could have stretched to cosmic proportions during the universe's rapid growth, only to snap shut as expansion slowed, leaving behind only gravitational echoes. Others might have stabilized at quantum sizes, threading the vacuum of space like invisible spider silk, too small to detect but woven into everything. There's even a spine-tingling possibility that dark matter, the invisible glue holding galaxies together, could be the ghostly remnants of these collapsed tunnels, their gravitational pull lingering long after their structures evaporated. The hunt for these relics isn't just academic. If a stable primordial wormhole survives, it could be a time capsule from the universe's first seconds, preserving conditions no accelerator on Earth can recreate. Passing through one might offer a glimpse of physics before the laws as we know them crystallized a window into a time when gravity and quantum forces were still entwined. Or perhaps they've decayed into something stranger, cosmic fuzzballs, their entrances disguised as ordinary black holes, their interiors hiding bridges to other epochs. The universe's oldest shortcuts might not look like tunnels at all, but like puzzles waiting for a civilization clever enough to read the clues written in the sky's oldest light. For now, the search continues. Next-generation telescopes like the Simons Observatory are scanning the CMB with unprecedented precision, hunting for the subtle distortions that could betray a wormhole's touch. Others are sifting through gravitational wave data, listening for the faint tremors that might ripple from a primordial tunnel's collapse. If they're found, it wouldn't just rewrite our understanding of wormholes, it would rewrite cosmic history itself, revealing a universe born threaded with hidden connections, its infancy far more tangled than we ever dreamed. What if the universe's greatest mystery, dark matter, has been hiding in plain sight, woven into the fabric of spacetime itself? Among the most radical theories in modern cosmology is the idea that dark matter, that invisible glue holding galaxies together, might not be made of exotic particles at all. Instead, it could be a vast, hidden network of wormholes, their gravitational shadows masquerading as missing mass. Picture this: every galaxy cloaked in a spiderweb of cosmic tunnels, too small or diffuse to see directly, but collectively bending light and tugging on stars in ways that mimic the effects of dark matter's elusive pull. The math behind this idea is as elegant as it is mind-bending. General relativity tells us that any concentration of mass or energy warps space-time, and wormholes, by their very nature, are twists in that fabric. Even if these tunnels are microscopic or stabilized by exotic physics, their combined gravitational influence could add up. Imagine pouring a fine mist of sand over a sheet of paper. Individually, each grain barely weighs it down, but together they create a noticeable curve. Now replace the sand with countless tiny wormholes, scattered like cosmic cobwebs across galaxy clusters. Their cumulative gravity might explain why we measure more mass than we can see, why galaxies rotate faster than visible matter alone should allow, or why light bends around seemingly empty patches of space. Some models take this further, suggesting these wormholes might not be random. They could form intricate, dark highways with dense nodes around galactic centers where gravity naturally funnels them. This could explain why dark matter seems to clump in halos around galaxies, its distribution eerily smooth yet oddly structured. Observations of gravitational lensing, where light bends around invisible mass, sometimes reveal anomalies that particle-based dark matter struggles to explain, unexpected filaments, asymmetries, or gaps. A wormhole network would naturally produce these quirks, its tunnels warping space-time in ways a diffuse particle cloud wouldn't. But how would such a network arise? One possibility lies in the early universe. During cosmic inflation, quantum fluctuations might have birthed not just galaxies, but space-time defects, tiny wormholes sprouting like weeds in the expanding fabric. As the universe cooled, these tunnels could have multiplied, threading through matter like invisible roots. Another theory ties them to black holes. If primordial black holes formed in the Big Bang's aftermath, their evaporation or collisions might have left behind wormhole remnants, too small to traverse but numerous enough to shape the cosmos. The most tantalizing implication: if dark matter is wormhole-rich, we might finally detect it not by spotting particles in a lab, but by mapping space-time's subtle wrinkles. Future gravitational wave observatories could catch echoes of wormhole vibrations, faint ripples in the cosmic web. Or next-generation telescopes might spot bizarre lensing patterns, where light bends around invisible tunnels instead of halos. Even more intriguing, if these wormholes link distant regions, their presence could subtly alter how galaxies move, creating flows and currents in the dark matter sea that betray their hidden structure. Of course, skeptics raise valid concerns. Wormholes require exotic matter or extreme conditions to stay open, and a universe teeming with them would need a mechanism to prevent collapse. Yet if even a fraction of dark matter's signatures stem from spacetime's hidden plumbing, it would revolutionize our understanding of both gravity and the cosmos's architecture. The universe's darkest secret might not be a particle waiting to be found, but a labyrinth of doors we've yet to learn how to see. Building a wormhole with our current technology sounds about as feasible as constructing a ladder to the moon, yet the blueprints already exist, sketched in the language of physics. Kip Thorne's pioneering work in the 1980s laid the foundation for these cosmic engineering projects, proposing that a traversable wormhole would need two key ingredients: a throat lined with exotic matter and a geometry precise enough to prevent collapse. Think of it like building a tunnel through a mountain, except the mountain is made of space-time, and the support beams must be crafted from a substance that defies gravity itself. Exotic matter isn't just rare, it's theoretical. Unlike normal matter, which attracts via gravity, this stuff would repel, acting as cosmic scaffolding to keep the wormhole's throat propped open. Calculations suggest you'd need a staggering amount of it, comparable to the mass energy of Jupiter, compressed into a structure just a few meters wide. And here's the catch: the only known source of negative energy is the quantum vacuum, where fleeting particles flicker in and out of existence. Harnessing enough of this energy would require technology capable of manipulating vacuum fluctuations on scales we can barely imagine, like bottling a thunderstorm in a teacup. But physicists aren't easily discouraged. Recent proposals suggest we might not need exotic matter at all, just lasers and quantum trickery. The idea hinges on quantum tunneling, where particles seemingly teleport through barriers they shouldn't be able to cross. Scale this up, and you could theoretically twist spacetime into a microscopic wormhole using ultra-high-intensity lasers to create a bubble of distorted vacuum. The energy demands are still astronomical. Think all the power output of a star focused into a beam smaller than an atom, but at least it swaps mythical matter for known physics. The engineering hurdles, though, are cosmic. Even if you could stabilize a wormhole, controlling its endpoints would be like threading a needle in a hurricane. Place one mouth near Earth and tidal forces could rip continents apart. The other end, a slight miscalculation might dump you into a star or a black hole. And then there's the feedback problem. Any matter or energy passing through would perturb the wormhole's structure, potentially triggering a collapse mid-transit. Some models propose using force fields or quantum locks to isolate the tunnel, but that's like asking a medieval blacksmith to build a particle accelerator. Perhaps the wildest idea comes from futurists who speculate that advanced civilizations might grow wormholes like crystals, nurturing them in high-energy accelerators or the cores of neutron stars. Others imagine harvesting cosmic strings, those space-time flaws left over from the Big Bang, as natural scaffolding. But for now, these are dreams scribbled at the edge of known physics, where the line between engineering and poetry blurs. The universe might permit wormholes, but it doesn't hand out construction permits easily. Every blueprint comes with a warning label: handle with care, contents may unravel reality. In the tangled web of quantum mechanics and general relativity, a startling idea has emerged. What if the spooky connection between entangled particles is actually a tiny wormhole in disguise? This is the heart of the ER equals EPR conjecture, a radical proposal that Einstein's two greatest theoretical headaches might secretly solve each other. On one side, you have the Einstein-Rosen bridge, the original wormhole born from relativity's equations. On the other, the EPR paradox, Einstein's famous objection to quantum entanglements, spooky action at a distance. At first glance, they seem unrelated. One describes tunnels through spacetime, the other an instantaneous bond between particles. But delve deeper, and the math whispers they might be two sides of the same cosmic coin. Take the black hole information paradox, one of physics' most infamous puzzles. When matter falls into a black hole, quantum mechanics insists the information it carries can't truly vanish, yet relativity says it's lost behind the event horizon forever. Theorists like Juan Maldacena and Leonard Susskind realized that if entangled particles straddling a black hole's edge were linked by microscopic wormholes, information could escape without breaking any rules. Picture two entangled particles as cosmic telegraph operators, one outside the black hole, the other inside. Normally, no signal can cross the event horizon, but if their entanglement is physically a wormhole, information could flow through this hidden channel, preserving quantum laws while respecting relativity's limits. This isn't just mathematical poetry. In the anti-de Sitter space models favored by string theorists, the equations map perfectly. Entangled qubits on a black hole's boundary correspond geometrically to wormholes threading its interior. It's as if the universe uses wormholes as its error correction code, ensuring no data ever gets truly deleted. The implications ripple outward. If every pair of entangled particles shares a Planck-scale wormhole, then the quantum vacuum, the empty space teeming with virtual particles, might be a seething network of ephemeral tunnels, constantly flickering into existence and vanishing like foam on a quantum sea. Yet for all its elegance, ER equals EPR raises dizzying questions. If entanglement is a wormhole, what happens when we measure one particle and collapse its state? Does the tunnel snap shut like a pair of cosmic scissors? Experiments with quantum teleportation, where entanglement transmits information, hint that the connection persists until observation breaks it. But nobody's spotted a wormhole in the lab. Some physicists argue this is because they're too small or unstable. Others suggest we're looking for the wrong signatures. If space-time is fundamentally pixelated at the quantum level, these wormholes might not resemble the smooth tunnels of relativity, but jagged quantum handshakes visible only through their gravitational whispers. The conjecture also redefines what a wormhole could be. Instead of a celestial subway, it might be more like a quantum zip file, a compact, information-dense link where spacetime itself encodes the connection. Advanced civilizations wouldn't need exotic matter to build wormholes. They'd just need perfect control over entanglement, weaving particles into macroscopic bridges. Imagine a future where quantum engineers stitch spacetime by entangling atoms in precise patterns, folding the universe like origami to bring distant points together. But the grandest implication lies in unification. For decades, relativity and quantum mechanics have been at war, one painting spacetime as smooth and deterministic, the other as grainy and probabilistic. If entanglement's magic is wormholes in disguise, then spacetime itself might emerge from a deeper quantum network, like a 3D hologram projected from entangled data on the universe's boundary. The AR equals EPR conjecture doesn't just offer a new way to see wormholes, it suggests they might be the missing stitches in the fabric of reality itself, weaving together the cosmos at its most fundamental level. Neutron stars are cosmic extremes, collapsed cores of dead stars so dense that a teaspoonful of their material would weigh 1 billion tons on Earth. But what if these stellar corpses hide more than just mind-bending density? Buried in their cores where gravity warps spacetime into knots, nature might have forged wormholes, natural tunnels threaded through the fabric of reality itself. Picture the heart of a neutron star, matter crushed beyond recognition, protons and electrons fused into a sea of neutrons, all squeezed into a city-sized sphere spinning faster than a kitchen blender. Under these conditions, general relativity suggests spacetime could twist so severely that it pinches shut, then reconnects elsewhere like a rubber band stretched so tight it snaps into a loop. The math is tantalizing. Simulations of neutron star interiors reveal that under certain conditions, particularly in magnetars, the ultramagnetic cousins of neutron stars' quantum effects might stabilize microscopic wormholes. These wouldn't be the galaxy-spanning tunnels of sci-fi. They'd be subatomic shortcuts, possibly linking different regions of the star's core or even threading through higher dimensions predicted by string theory. The key lies in the star's incomprehensible pressure. Normally, a wormhole's throat collapses instantly under its own gravity, but inside a neutron star, the outward push of degenerate neutrons, particles packed shoulder to shoulder like commuters in a subway crush, could counterbalance that collapse, acting like nature's own exotic matter. Detecting these hidden tunnels would require astrophysical sleuthing. One telltale sign: anomalous glitches in a neutron star's rotation. These ultra-precise cosmic clocks occasionally speed up or slow down without warning, and while most glitches are blamed on starquakes or superfluid vortices, some theorists propose that microscopic wormholes near the core could momentarily alter the star's moment of inertia, like a spinning ice skater tucking in an arm, except the arm is a spacetime tunnel. Others suggest looking for bursts of gravitational waves with unexpected frequencies, as collapsing or vibrating wormholes might emit ripples in the fabric of spacetime itself. The wildest possibility: some neutron stars might not be stars at all. A handful of observed objects like the mysteriously heavy neutron star PSR J0740 plus 6620 have masses so extreme they flirt with the theoretical limit before collapsing into black holes. What if they've already crossed that line, but their cores harbor wormholes that siphon off enough mass to delay the collapse? These quasi-black hole objects could appear almost identical to neutron stars, their true nature hidden until a probe plunges into their depths or until their wormholes snap shut in a flash of gamma rays. Yet the risks of probing are as colossal as the rewards. Disturbing a neutron star's core could trigger a chain reaction, releasing enough energy to sterilize a solar system. And if a wormhole inside one connects to somewhere unpredictable, the consequences could range from cosmic to catastrophic. Still, the allure is irresistible. If neutron stars do cradle wormholes in their hearts, they'd be nature's gift to physics' pre-built cosmic shortcuts, forged in stellar furnaces, waiting for a civilization brave enough to reach inside. Until then, we watch and listen, decoding the whispers of these dense, dead stars for hints of the tunnels they might hide. If wormholes exist as stable, traversable tunnels, they wouldn't just be isolated curiosities. They could form the backbone of a cosmic transit system, linking galaxies like stops on an intergalactic subway. Picture a civilization so advanced that hopping from the Milky Way to Andromeda isn't a journey of millions of years but a commute shorter than a lunch break. This isn't just sci-fi fantasy, it's a plausible endgame for a Kardashev-type Roman III civilization, one that harnesses the energy of entire galaxies. To them, wormholes wouldn't be rare anomalies but infrastructure, meticulously maintained and strategically placed like highway rest stops across the universe's sprawl. The logistics of such a network would be staggering. First, you'd need to stabilize each wormhole, likely using exotic matter or quantum fields to reinforce their throats against collapse. Then comes placement. Entrances would have to orbit safely far from stars or black holes to avoid gravitational disruptions. One miscalculation and a wormhole near a galactic core might stretch into a deadly funhouse mirror, shredding anything that enters. But for a civilization mastering space-time engineering, these could be routine challenges like ancient Romans paving roads or modern engineers tunneling through mountains. The real brilliance lies in the network's efficiency. Unlike warp drives or generational ships which demand constant energy to move through space, a wormhole highway would be a one-time construction project with perpetual returns. Need to colonize a galaxy a billion light-years away? Just extend the network, threading new tunnels like laying railroad tracks. Over millennia, entire clusters of galaxies could become interconnected, with trade, communication, and even cultural exchange flowing as effortlessly as data through fiber optics. But who's to say this hasn't already happened? Some theorists speculate that unexplained cosmic structures like odd gaps in galaxy distributions or strangely aligned quasars might betray the presence of a hidden wormhole grid. If an ancient civilization built such a system eons ago, its relics could still linger, camouflaged as natural phenomena. The most tantalizing hint might lie in fast radio bursts, those mysterious high-energy signals from deep space. While most have natural explanations, a handful exhibit patterns that defy easy classification. Could these be navigation beacons or maintenance pulses from a wormhole transit system long abandoned or still in use? Of course, the risks of cosmic commuting are as vast as the rewards. A wormhole hub near a bustling galaxy might become a battleground if civilizations clash over control. And then there's the existential dread of network failure. If a key wormhole collapses, entire galactic sectors could be severed like islands cut off by a storm. Yet for a species thinking in million-year timescales, these are just engineering puzzles waiting to be solved. The universe may have forged the first wormholes, but intelligence could turn them into something greater. Not just shortcuts through space, but the streets and bridges of a connected cosmos. Einstein showed us time is elastic, stretching and compressing depending on motion and gravity, but combine that with a wormhole and the elasticity becomes a gateway to the past. Imagine one end of a wormhole parked safely near Earth while the other hurtles away at nearly light speed. According to Kurt Gödel's solutions to Einstein's equations, that moving end would experience drastic time dilation. A single hour for the traveling mouth could equate to decades back on Earth. Now picture stepping through the Earth-side entrance in the year 2100 and emerging from the high-speed end just a year after it left, effectively catapulting yourself a century into your own past. It's the ultimate cosmic rewind button, bending the arrow of time into a loop. This scenario mirrors the classic twin paradox, where one astronaut traveling near light speed returns to find their Earth-bound sibling aged far more than them. Except here, the wormhole turns the thought experiment into a one-way time machine. The paradox gets even stranger if you attempt round trips. Jump back to the past through the wormhole, then board a conventional ship to reach the high-speed mouth before it departed, and you could theoretically hand your past self a message before they even entered the tunnel. The universe despises such loops, hence Stephen Hawking's chronology protection conjecture, but Gödel's math suggests nature might grudgingly allow them under extreme conditions. The catch: controlling these relativistic wormholes would demand precision bordering on the impossible. Even slight miscalculations could strand you in an unintended era, or worse, unspool the wormhole itself. A mouth accelerated too violently might stretch into a singularity, snapping the tunnel shut mid-transit. Others speculate that quantum effects would amplify near the time-dilated exit, flooding the wormhole with lethal radiation. And then there's the existential question. If time travel via wormholes is possible, where are the tourists from the future? The silence might imply nature has safeguards we've yet to uncover, or that surviving the trip requires physics so advanced it's indistinguishable from magic. Yet the implications are too tantalizing to ignore. A civilization mastering relativistic wormholes wouldn't just explore space, they'd curate history itself. Imagine archives where scholars stroll into wormholes to witness ancient events firsthand, or rescue missions retrieving doomed colonies from the past. But with such power comes peril. A single misused time tunnel could unravel causality, spawning paradoxes that fracture reality. Perhaps this explains why the cosmos hides these shortcuts behind layers of relativistic chaos. Time travel might not be impossible, just reserved for those wise enough not to break the universe with it. When two black holes spiral toward collision, the universe doesn't just witness a cataclysm, it might briefly stitch open a doorway. Recent supercomputer simulations reveal that under the right conditions, a black hole merger could twist space-time so violently that a wormhole flickers into existence for the tiniest fraction of a second. Picture the final moments before impact. The holes stretch and distort each other's event horizons like taffy in a cosmic tug-of-war. As they merge, simulations suggest their singularities might not just combine. They could momentarily punch through the fabric of spacetime, forming a tunnel before collapsing into a new black hole. It's as if the universe itself experiments with shortcuts, sewing them into reality during moments of extreme chaos. These short-lived wormholes wouldn't be the stable tunnels of sci-fi dreams. They'd be cosmic mayflies, surviving for mere milliseconds before gravity's grip crushes them shut. Yet even that fleeting existence could leave fingerprints, subtle echoes hidden in the gravitational waves rippling outward from the collision. When LIGO detects a black hole merger, the signal typically resembles a chirp, a rising tone that abruptly cuts off as the new black hole forms. But some physicists argue that if a wormhole briefly formed, the gravitational waves might carry faint after ripples, like a bell's resonance after the initial strike. These echoes could betray the tunnel's presence, hinting at structures far stranger than black holes alone. The challenge: distinguishing these whispers from noise. LIGO data is already packed with cosmic static vibrations from neutron stars, distant supernova, even quantum jitter in the detectors themselves. Isolating wormhole echoes would be like picking out a single violin's note in a thunderstorm. Some researchers have claimed tentative detections, pointing to anomalies in signals like GW 150,914, the first black hole merger LIGO observed. Others remain skeptical, noting that alternative explanations like black holes with unusual shapes or spin rates could produce similar wave patterns. The debate hinges on a deeper question: does space-time, when pushed to its limits, favor black holes as endpoints, or does it allow for more exotic possibilities, even fleetingly? The implications stretch beyond mere curiosity. If mergers can birth wormholes even ephemerally, it suggests these tunnels might be woven into the universe's most violent events. Advanced civilizations could theoretically exploit such moments, using directed energy or quantum tricks to stabilize the wormhole before it collapses. Imagine a species that doesn't build wormholes from scratch, but lurks near colliding black holes, ready to hijack nature's own shortcuts. More fundamentally, these events could test whether wormholes are mathematical curiosities or genuine features of reality. Every black hole collision might be a cosmic lab forging wormholes in its fury, if only we know how to listen for their birth cries. The next generation of gravitational wave detectors, like the space-based LISA mission, could settle the debate. With sensitivity tuned to lower frequencies, LISA might catch the longer-lasting echoes that LIGO misses, or spot mergers involving intermediate mass black holes, prime candidates for spawning larger, longer-lived wormholes. Until then, the collisions we've observed remain tantalizingly ambiguous, their signals holding secrets we're just beginning to decode. Black holes might not be the universe's only gravitational monsters. Hidden in their mergers could be the ghosts of wormholes flickering in and out of existence, teasing us with the possibility that even death throes can birth doorways. Empty space isn't really empty, it's a seething quantum playground where particles flicker in and out of existence, borrowing energy from the vacuum before vanishing again. This cosmic churn, known as zero-point energy, might be doing more than just filling the void. It could be stitching space-time itself into transient wormholes, microscopic tunnels bubbling up like quantum foam and disappearing before we can blink. Imagine the vacuum as a pot of boiling water, with wormholes forming like steam bubbles, each a fleeting gateway between points that might lie light years apart in our familiar 3 dimensions. The key to this idea lies in the Casimir effect, a bizarre quantum phenomenon we've actually observed in labs. Place 2 metal plates unfathomably close together in a vacuum, and the plates get pushed toward each other by an invisible force. Why? Because the space between them becomes too narrow for certain quantum fluctuations to fit, creating a pressure imbalance. This proves that the vacuum isn't passive, it's alive with energy that can bend reality. Now scale that up. If quantum fluctuations can warp spacetime enough to move plates, could they also twist it into microscopic wormholes? The math suggests yes, but these wouldn't be the sturdy tunnels of sci-fi. They'd be quantum fireflies, flashing into existence for fractions of a second before collapsing under their own instability. Stabilizing these ephemeral portals is where physics hits a wall. To keep a quantum wormhole open long enough for anything to traverse it, you'd need to somehow freeze the vacuum's fluctuations, imposing order on chaos. One speculative proposal involves using ultra-intense electromagnetic fields to coax the vacuum into a coherent state, like calming a stormy sea into a mirrored surface. Another suggests manipulating dark energy, the universe's accelerating force, to counteract the wormhole's collapse, but both approaches demand energies and control far beyond our current reach, like trying to sculpt smoke with your bare hands. The wild card here is entanglement. If the ER=EPR conjecture holds that entangled particles are connected by Planck-scale wormholes, then the vacuum's endless particle-antiparticle pairs might be laced with invisible tunnels already. Harnessing them wouldn't require building wormholes from scratch, but finding a way to grow these natural threads into macroscopic structures. Picture a civilization that learns to knit spacetime by entangling vast clusters of particles, weaving quantum threads into a traversable fabric. Yet, even if we could stabilize a vacuum wormhole, the journey might be unusual. Crossing a tunnel forged from quantum foam could feel less like stepping through a door and more like being disassembled into probabilities, your information scrambled and rebuilt on the other side. It's the ultimate cosmic tightrope walk, balanced between existence and oblivion, where the line between transportation and teleportation blurs into quantum uncertainty. For now, vacuum wormholes remain tantalizing ghosts, their existence hovering at the edge of theory and experiment. But if they're real, they'd redefine the very nature of emptiness, revealing a universe where even the void hums with hidden doorways, waiting for someone to learn the right knock. What if consciousness isn't confined to the brain but woven into the fabric of spacetime itself, with wormholes as the invisible threads? Among the most daring theories bridging physics and neuroscience is the idea that our minds might harness microscopic spacetime tunnels to achieve what neurons alone can't: unity of experience. At the heart of this radical proposal lies the Penrose-Hameroff theory of orchestrated objective reduction, a framework suggesting that consciousness arises from quantum processes in the brain's microtubules, tiny protein structures inside neurons. But here's where it gets wild. These quantum vibrations might not just flicker within cells. They could resonate through Planck-scale wormholes, connecting disparate brain regions into a seamless whole. Picture this: every thought, every burst of awareness could involve quantum states collapsing in sync across billions of neurons, their coordination enabled by spacetime's hidden shortcuts. It's as if the brain isn't just a computer but a quantum orchestra, with wormholes conducting the symphony. Roger Penrose, the Nobel-winning physicist who pioneered this idea with anesthesiologist Stuart Hameroff, argues that classical physics alone can't explain the binding problem: how scattered neural activity coalesces into a single, unified experience. But if spacetime itself is granular at the quantum level, with wormholes stitching together its fabric, then consciousness might be riding these ripples, weaving subjectivity from the universe's underlying geometry. The math hints at something extraordinary. In models inspired by string theory and loop quantum gravity, microtubules could exploit spacetime's foam-like structure, their quantum vibrations poking tiny wormholes into existence. These tunnels wouldn't be traversable in the traditional sense. They'd be more like quantum Velcro, briefly binding distant neural events into a coherent moment of awareness. Imagine two neurons firing on opposite sides of the brain. Instead of relying solely on sluggish chemical signals, their quantum states could tunnel through a microscopic wormhole, sinking instantaneously across what would normally be an impassable divide. Critics, of course, pounce on the speculative nature of these ideas. No experiment has yet detected quantum coherence in warm, wet brain tissue, let alone wormholes mediating it. And even if microtubules do house quantum vibrations, how they'd avoid decoherence, the noisy disruption of quantum states by their environment, remains a thorny puzzle. Yet proponents counter with tantalizing clues. Certain anesthetics, which selectively shut down consciousness, appear to target microtubules precisely, silencing their quantum oscillations without halting broader neural activity. If consciousness were purely classical, why would these tiny structures matter so much? The implications spiral beyond biology. If wormholes underpin consciousness, then subjective experience might not be unique to carbon-based life. Advanced AI built on quantum processors could develop inner lives, their thoughts threading through synthetic spacetime tunnels. Alien species might evolve entirely different neural architectures, yet share the same quantum spacetime foundation for awareness. Even the universe itself, if permeated by these microscopic tunnels, could possess a proto-consciousness, a cosmic mind emerging from the dance of its smallest structures. For now, these ideas hover at the edge of science, where hard data meets philosophical wonder. But they remind us that wormholes might not just bridge stars, they could be the invisible scaffolding of thought itself, stitching together the most intimate fabric of existence, the moment when electrical sparks become a symphony of self. Whether the theory holds or collapses under scrutiny, it dares us to ask, could the universe's grandest shortcuts be hiding in the quiet depths of our own minds? Black holes are cosmic enforcers of modesty, their singularities forever veiled behind event horizons, hidden from prying eyes. This concept, dubbed cosmic censorship, is physics' way of saying the universe abhors a naked singularity, a point of infinite density exposed for all to see. But what if wormholes are the ultimate sensors, nature's solution to these space-time pathologies? Imagine a singularity beginning to form without the protective cloak of an event horizon. Before it can bear its infinite curves to the universe, space-time might twist itself into a wormhole, stitching the singularity safely away like a cosmic tailor covering a tear in reality's fabric. This elegant fix isn't just theoretical hand-waving. The math of general relativity shows that under certain conditions, a forming singularity could naturally warp into a wormhole throat, connecting to another region of spacetime instead of collapsing into an exposed infinity. It's as if the universe has fail-safes when gravity threatens to rip spacetime too brutally. Wormholes emerge as damage control, smoothing over the worst violations of physics rules. Some models even suggest that every black hole singularity might secretly be the mouth of a wormhole, forever hidden behind its event horizon. The singularity isn't gone, it's just been relocated, tucked neatly into the tunnel's geometry where it can't wreak havoc on causality. But there's a dark twist to this cosmic censorship. While wormholes might hide singularities from view, they could become singularities themselves under the wrong conditions. Picture a wormhole stretched too thin by tidal forces or overloaded with energy its throat could pinch off into a new singularity, birthing a fresh spacetime disaster. This creates a paradoxical balancing act. A wormhole must be stable enough to censor its contents, yet not so unstable that it collapses into the very thing it's meant to conceal. The universe seems to walk this tightrope by threading wormholes with exotic matter, the negative energy acting like a counterweight to gravity's crushing grip. The implications ripple across astrophysics. If wormholes truly serve as cosmic sensors, they might explain why we've never observed naked singularities, even in extreme environments like colliding black holes or the Big Bang's aftermath. They'd also redefine what lurks inside black holes, not a dead-end infinity, but a gateway to somewhere or someone else. Yet the censorship isn't perfect. Quantum fluctuations near a wormhole's throat could momentarily expose flickers of the hidden singularity, like static tearing through a TV screen's image. These glimpses might be our only way to detect wormholes indirectly, searching for the cracks in spacetime's censorship. Perhaps most unsettling is the idea that censorship can fail. In universes with different physical constants or higher dimensions, naked singularities might run rampant, their infinite energies unraveling causality. Wormholes could be our universe's unique solution, a delicate compromise between order and chaos. For now, the debate rages. Are wormholes spacetime's guardians, or do they merely delay the inevitable? The answer might lie in the next generation of gravitational wave detectors, listening for the whispers of hidden singularities, or the absence where wormholes have silenced them forever. The searing, swirling chaos inside a fusion reactor might seem worlds apart from the serene vastness of spacetime, but peer closer and you'll find uncanny parallels. In labs worldwide, physicists working with superheated plasma, the fourth state of matter where electrons tear free from atoms, are accidentally creating structures that behave startlingly like wormholes. Tokamaks, those donut-shaped chambers designed to harness star power here on Earth, generate magnetic fields so twisted they fold plasma into knots resembling theoretical spacetime tunnels. Meanwhile, high-intensity lasers blasted through plasma can carve out ephemeral channels where particles seem to teleport from one point to another, defying classical motion. It's as if the universe encoded its grand cosmic shortcuts into the very fabric of energized matter, waiting for us to notice. Take the bizarre phenomenon of plasma filaments. When certain fusion experiments reach critical energy thresholds, thin tendrils of ionized gas suddenly self-organize into braided strands, threading through the chaos like cosmic knitting needles. Peer-reviewed simulations from institutions like Princeton's Plasma Physics Lab reveal these filaments aren't just visually striking, their mathematical profiles eerily match the curvature of Morris Thorne wormholes, those hypothetical traversable tunnels from general relativity. The filament's hollow cores even exhibit negative effective pressure, mimicking the repulsive effects of exotic matter needed to prop a wormhole open. Of course, these plasma structures exist for microseconds before fizzling out, but their transient existence hints that spacetime's trickery might be hiding in plain sight, echoed in the whirl of man-made stellar fire. Laser experiments add another layer to the mystery. When petawatt lasers pulse through plasma, they rip electrons away at near light speed, creating Wakefield's waves of electric charge that surf through the ionized gas. In recent Nature-published studies, researchers observed particles disappearing from one point in the plasma and reappearing millimeters away without traversing the intervening space. The leading explanation involves quantum tunneling, but some theorists suggest these hops could be microscopic analogs of spacetime shortcuts. The laser's extreme energy warps the plasma's effective geometry, much like a concentrated mass warps spacetime, potentially creating fleeting wormhole-like corridors where the usual rules of distance break down. The implications ripple beyond theory. If plasma can mimic wormhole dynamics, we might not need to peer into deep space to test traversability. We could engineer tabletop experiments using tweaked tokamak configurations or laser arrays. One tantalizing proposal involves stacking ultra-thin plasma layers to simulate higher dimensional spacetime, a nod to string theory's hidden dimensions. By tuning the plasma's density and magnetic fields, physicists might someday recreate a toy version of a Kaluza-Klein wormhole, a tunnel piercing through hypothetical compactified dimensions. These experiments wouldn't just illuminate cosmology, they could revolutionize energy science, revealing how to stabilize plasma instabilities that currently hinder fusion reactors. Yet the parallels have limits. Plasma wormholes exist in electromagnetic fields, not gravitational spacetime, and their lifetimes are measured in nanoseconds. Still, the kinship between these lab-born phenomena and Einstein's equations is too striking to ignore. Whether a happy coincidence or a hint of deeper physics, these experiments blur the line between astrophysics and engineering, suggesting that the universe's most exotic structures might have humble cousins dancing in our fusion chambers. The next breakthrough in wormhole science might not come from a telescope, but from a reactor where the raw power of artificial stars whispers secrets about the cosmos' hidden shortcuts. Where are all the aliens? The Fermi paradox has haunted astronomers for decades. If the universe is so vast and ancient, why does it seem so empty? One unsettling answer might be hidden in the very fabric of spacetime itself. Imagine civilizations so advanced they don't just travel between stars, they bypass them entirely, slipping through wormholes like shadows through a crack in the door. These wouldn't be the clunky warp drives or generational ships we imagine. They'd be masters of spacetime engineering, using cosmic shortcuts to move undetected, leaving no traces of their passage for telescopes or radio receivers to catch. This idea dovetails eerily with the zoo hypothesis, the notion that extraterrestrial societies deliberately avoid contact, treating Earth like a nature preserve or a lab experiment. But instead of lurking in distant star systems, they could be closer than we think, observing through wormhole-linked probes or even folding space to study us from unseen vantage points. Think of it like ants on a sidewalk, oblivious to a researcher peering through a microscope from a lab miles away. The microscope, in this case, a wormhole's throat, stretching across light years while masking its presence. The darker twist comes from the dark forest theory, where civilizations hide because broadcasting your location invites destruction. In this ruthless cosmic game of hide and seek, wormholes wouldn't just be tools for travel, they'd be survival tech. An advanced species might dismantle their star systems to power wormhole networks, vanishing into a web of tunnels that defy detection. No radio emissions, no Dyson swarms, just silent, untraceable mobility. It's the ultimate stealth mode. Why fly through the galaxy when you can sidestep it entirely, emerging only in shielded enclaves or resource-rich corners of spacetime? Evidence, or rather the lack of it, might already be staring us in the face. Unexplained gravitational anomalies, places where light bends oddly without a visible cause, could be the gravitational shadows of cloaked wormhole mouths. Even stranger are matched cosmic events, gamma-ray bursts or supernova that repeat with impossible symmetry across the sky, as if something is stitching distant points together. And then there's the eerie silence of the cosmos itself, a quiet that feels less like emptiness and more like a crowd holding its breath. Yet the most chilling possibility isn't that aliens use wormholes to hide from us, it's that they've learned to hide from something else. If civilizations older than galaxies exist, their wormhole networks might not just be highways but bunkers, shielding them from existential threats we can't yet fathom. The universe's silence wouldn't be a puzzle, it'd be a warning written in the negative space between stars. Wormholes, then, aren't just answers to the Fermi paradox, they're the locked doors of a cosmos where everyone has learned to whisper. Neutrinos are the universe's ultimate ghosts, particles so ethereal they pass through entire planets as if they weren't even there. But what if these spectral particles, when concentrated into ultra-high-energy beams, could rip the fabric of spacetime itself? At the Ice Cube Observatory buried deep in Antarctic ice, scientists have detected neutrinos with energies so extreme, exceeding 1 peta-electronvolt, that their collisions might briefly warp reality into microscopic wormholes. These wouldn't be the grand interstellar tunnels of science fiction. They'd be quantum-scale punctures, flickering into existence for fractions of a nanosecond before vanishing like bubbles in a cosmic champagne glass. The math behind this idea stems from an audacious marriage of particle physics and general relativity. When a neutrino with energy comparable to a baseball pitch approaches another particle, its concentrated energy density could, for an instant, mimic the gravitational curvature of a tiny black hole. But instead of collapsing into a singularity, certain quantum gravity models suggest spacetime might bounce at these scales, forming an ephemeral wormhole throat between the collision points. It's as if the universe, faced with such concentrated energy, briefly folds rather than tears. The Ice Cube team has already observed over 100 of these ultra-high-energy neutrino events, some with properties that defy standard particle interactions. Could subtle anomalies in their data, like missing energy or unusual decay patterns, be fingerprints of spacetime itself warping under the strain? Experiments at CERN Large Hadron Collider add fuel to the fire. When smashing lead nuclei at near light speed, detectors have recorded moments where particles seem to disappear from one collision point and reappear millimeters away without traversing the intervening space. The official explanation involves exotic quark-gluon plasma behavior, but a handful of theorists propose an alternative. The collisions might spawn Planck-scale wormholes that instantly reconnect elsewhere in the detector. These wouldn't be traversable by anything larger than a quantum fluctuation, but their gravitational aftershocks could subtly alter particle trajectories, an effect some argue has already been glimpsed in LHC's strangest outlier events. The real breakthrough would come if we could intentionally create and measure such phenomena. Proposed upgrades to Ice Cube, combined with next-generation neutrino beams like those at Fermilab's Dune experiment, might achieve the necessary energies to test the wormhole hypothesis directly. Picture a neutrino gun firing pulses through Earth to a detector thousands of miles away, with ultra-precise timing measuring whether any particles arrive infinitesimally early, a telltale sign they took a shortcut through a wormhole's twisted geometry. Other proposals involve entangled neutrinos. If their quantum connection is mediated by microscopic wormholes, as the ER equals EPR conjecture suggests, then manipulating their states could indirectly probe spacetime's hidden plumbing. Yet skeptics raise valid concerns. Even if neutrinos can spawn wormholes, they'd be so tiny and fleeting that their practical use seems negligible. And without a unified theory of quantum gravity, predicting their behavior remains speculative. But here's the twist. If nature allows wormholes to form at quantum scales, advanced civilizations might have learned to amplify them. Imagine a technology that stacks thousands of neutrino collisions in perfect sync, weaving microscopic tunnels into a macroscopic bridge, like using a billion tiny stitches to sew a fabric big enough to walk through. The universe's most elusive particles could hold the blueprint for its greatest shortcuts, hiding in plain sight within the very collisions we're already studying. Supersymmetry, the elegant yet unproven theory that every known particle has a hidden superpartner, might hold the key to wormholes far more stable than anything Einstein envisioned. Among these hypothetical particles, photinos stand out, shadowy cousins of photons with mass and quantum properties that could theoretically counteract gravity's crushing grip. Picture a wormhole's throat lined not with exotic matter, but with a dense fog of these photinos, their unique interactions generating just enough negative pressure to keep the tunnel propped open. It's a cosmic balancing act where particles we've never seen could solve a problem we've never fully cracked. The math behind this idea is as beautiful as it is speculative. Supersymmetry, SUSY, predicts a menagerie of new particle squarks, leptons, gluinos, each mirroring familiar matter but with quantum spins shifted by half a unit. When applied to wormhole physics, certain SUSY models suggest these superpartners could interact in ways that mimic the repulsive effects of exotic matter. For instance, photino's hypothetical fermionic partners of photons might form Bose-Einstein condensates under extreme conditions, creating regions where gravity effectively pushes instead of pulls. String theorists like Kamran Vafa have explored how such condensates could stabilize higher-dimensional wormholes, their gravitational footprints subtle enough to evade detection unless you knew exactly where to look. The Large Hadron Collider could be our best shot at testing these ideas indirectly. While SUSY particles remain conspicuously absent in LHC data so far, certain anomalies, like unexpected energy signatures in proton-proton collisions, might hint at their fleeting existence. If photinos or other superpartners are produced but immediately decay into invisible dark matter, their presence could be inferred from energy imbalances in detectors. Even more tantalizing, some SUSY models predict micro-black holes could form briefly in high-energy collisions. While none have been spotted, their absence might actually support wormhole scenarios. What if the energy required to create a black hole instead spawns a microscopic wormhole, siphoning particles into hidden dimensions? Critics argue SUSY failure to materialize at predicted energy scales undermines its connection to wormholes. Yet even if supersymmetric particles are heavier than anticipated, their hypothetical properties still offer a compelling framework for exotic physics. Modified theories like split SUSY, where some superpartners remain ultra-light, could preserve the photino's role in wormhole stabilization while accommodating experimental null results. The takeaway: SUSY might not be dead, just hiding in parameter spaces we've yet to explore thoroughly. The grander implication is philosophical. If nature indeed uses supersymmetry to knit spacetime seams, then wormholes could be less like cosmic accidents and more like deliberate features of a universe built on symmetry at its deepest level. Every unobserved photino becomes a whisper of hidden cosmic plumbing, waiting for a collision energetic enough to reveal the stitches holding reality together. Until then, SUSY remains a ghost story written in equations, one where the punchline might not be a particle, but a doorway. If the universe is destined to collapse in a fiery Big Crunch, a cosmic reversal of the Big Bang where everything contracts back into a singularity, then wormholes might become the universe's final lifelines. Picture spacetime itself shrinking like a deflating balloon, galaxies hurtling toward one another as gravity overpowers expansion. In this apocalyptic scenario, the very fabric of reality would warp under unimaginable pressure, and wormholes could emerge as nature's emergency exits, stitching together regions of the cosmos before they're crushed into oblivion. The math behind this idea is spine-tingling. As the universe contracts, the density of matter and energy would skyrocket, twisting space-time into knots so tight that shortcuts between distant points become inevitable. Wormholes wouldn't just exist in this collapsing cosmos, they'd dominate it, multiplying like cracks in ice as the temperature drops. But here's where the physics gets surreal. Unlike the delicate wormholes we imagine today, propped open by exotic matter or quantum tricks, these end-time tunnels would be forged by raw gravitational fury. The crushing weight of a collapsing universe could forcibly pinch space-time into bridges, like a baker kneading dough until seams form. Some models suggest these crunch-born wormholes might even stabilize naturally, their throats reinforced by the sheer density of energy around them. For a civilization clinging to survival, these tunnels could offer a desperate gamble. Leap through a wormhole to a region of the universe collapsing slightly slower, buying precious extra moments before the end. It's the ultimate cosmic delay tactic, like outrunning an avalanche by darting through hidden caves. Now contrast this with the Big Rip, a far lonelier demise where dark energy's grip grows so strong that it shreds space-time itself. In this scenario, the universe doesn't collapse, it frays. Galaxies, stars, even atoms would be torn apart as the fabric of reality stretches too thin. Wormholes here face a grimmer fate. Instead of flourishing under pressure, they'd stretch like taffy until their throats snap, evaporating into nothingness long before the final rip. The difference between these two dooms reveals something profound. Wormholes aren't just passive structures, but dynamic players in space-time's fate. They thrive in chaos, but only if gravity writes the rules. Let dark energy dominate, and the universe's shortcuts unravel like stitches in an unraveling sweater. The wildest possibility, a collapsing universe's wormholes might not just connect space, they could bridge time loops, allowing causality to twist back on itself. As the Big Crunch approaches, time itself would distort, with gravitational time dilation reaching extreme levels. A wormhole formed in these final moments might link not just two places, but two times, creating closed cycles where the universe's death feeds back into its birth. Some theorists speculate this could spawn a cyclical cosmos, where each Big Bang emerges from a wormhole in the previous universe's collapse. It's a poetic symmetry, wormholes as both the universe's last gasp and its first breath, threading existence into an endless ouroboros of creation and destruction. Yet for all their apocalyptic grandeur, these endgame wormholes might leave subtle clues today. If our universe is destined for a big crunch, current observations could reveal gravitational anomalies, regions where spacetime's curvature hints at latent instability. The cosmic microwave background might show faint imprints of wormholes formed in the early universe, their echoes lingering like premonitions. Or perhaps dark matter's odd clustering patterns betray the gravitational shadows of wormholes simmering beneath the surface, waiting for collapse to awaken them. The chilling takeaway: wormholes could be more than cosmic shortcuts, they might be the universe's contingency plan, woven into spacetime's blueprint for its own survival. Whether through crunch or rip, their fate is entwined with reality's ultimate destiny, revealing a cosmos that doesn't just have wormholes but might one day become them. The universe might already be running the most powerful computer imaginable, a vast network of wormholes crunching data through the fabric of spacetime itself. Think of a black hole's event horizon not as a one-way street to oblivion, but as a cosmic hard drive encoding information in its surface area like bits on a disk. Now stretch that idea further. What if wormholes, those twisted tunnels through space-time, aren't just shortcuts for travel, but circuits in a colossal quantum processor? The math suggests this isn't just fantasy. Every wormhole throat could act like a qubit, its quantum states entangled across light years, performing calculations at scales that would make today's supercomputers look like abacuses. At the heart of this idea lies black hole thermodynamics, where entropy, the measure of disorder, is directly tied to a black hole's surface area. Jacob Bekenstein and Stephen Hawking showed that black holes aren't just simple garbage compactors, they're information processors scrambling data into thermal radiation. Wormholes, if stable, could take this further. Their throats stretching between distant points might act like quantum gates, transmitting and transforming information through spacetime's geometry. Picture a network of wormholes threading the cosmos like synapses in a galactic brain, with gravitational waves or quantum fields serving as the signals pulsing through the system. The real magic happens with entanglement. Just as quantum computers on Earth rely on entangled qubits to perform parallel calculations, a wormhole network could exploit spacetime's inherent quantum links to process information non-locally. An input at one end, say a particle spin state, could instantaneously influence an output at the other end, bypassing light speed limits. It's the ultimate parallel processor. Instead of flipping bits in silicon, you're twisting the fabric of reality itself. Some theorists propose that advanced civilizations might not just use wormholes to travel. They could harness them to simulate entire universes or solve problems too complex for classical physics, like predicting cosmic evolution or decoding the unified theory of everything. But here's the catch: stability equals power. A wormhole quantum computer would need to balance gravitational collapse against quantum coherence, a feat requiring precision beyond anything we can engineer today. Black holes hint at how delicate this balance is. Their information processing is chaotic, like a CPU overheating. A functional wormhole processor would need to avoid this chaos, possibly by threading exotic matter through its structure like error-correcting code. The universe might have already built prototypes. Certain quantum gravity models suggest the Big Bang's aftermath could have birthed ephemeral wormhole circuits, their calculations etched into the cosmic microwave background like cosmic debugging logs. The implications spiral into philosophy. If spacetime itself can compute, then the cosmos might not just contain intelligence, it could be intelligence, a self-processing entity where wormholes are the neural pathways. Our own brains, with their 80 billion neurons, might be microscopic echoes of this grand design. Or perhaps we're nearing the horizon of comprehension, where physics blurs into metaphysics, and the universe's deepest secrets are written not in equations, but in the silent hum of spacetime's quantum gates. From the shimmering blue vortex of Stargate to the time-twisting cracks in Doctor Who's universe, wormholes have become sci-fi's favorite cosmic cheat code, a storytelling shortcut that bends not just space but our imaginations. These fantastical portals let heroes leap across galaxies in a single step, outrun apocalypses by hopping timelines, or even rewrite history by stepping through the wrong door at the right moment. But for all their cinematic spectacle, how much do these fictional wormholes resemble the tangled physics of Einstein's equations? The answer lies somewhere between artistic inspiration and outright rebellion against the laws of nature. Take Stargate's iconic ringed portal, where matter gets disassembled into energy, transmitted through a wormhole and reassembled on the other side. It's a brilliant workaround for the gruesome reality of traversing a real wormhole, where tidal forces would spaghettify anything attempting the journey. The show's writers traded gravitational nightmares for clean, plot-friendly teleportation, but buried a kernel of truth in the concept. Quantum teleportation experiments today do involve transferring information between entangled particles instantaneously, though scaling that up to human travelers remains firmly in fantasy territory. Compare that to Interstellar's Gargantua wormhole, meticulously modeled by physicist Kip Thorne to obey general relativity. Its shimmering, lens-like distortion wasn't just eye candy. It reflected how a real wormhole might bend light around its throat, warping the starfield into a halo of fractured galaxies. Then there's Doctor Who's time-traveling cracks in the universe, less wormholes than plot devices woven with whimsical hand-waving. The TARDIS famously travels through the time vortex, a dimension where past, present, and future swirl together like soup. While real wormholes could theoretically link different times if one end were accelerated to near light speed, the show's casual leaps through history prioritize drama over physics. Yet even here, there's a nod to real science, the weeping angels, creatures that displace victims through time by touching them, eerily mirror quantum theories where observation collapses probabilities into fixed outcomes, as if reality itself flinches when you blink. Star Trek takes a different tack with its subspace wormholes offering stable shortcuts between quadrants. The franchise often treats them like cosmic highways, complete with tolls, hello, Ferengi, and traffic jams. This bureaucratic approach hilariously mirrors real debates about who'd control a traversable wormhole: governments, corporations, space pirates, but Trek's biggest liberty is stability. Real wormholes would likely snap shut if you sneezed too hard near one, while Deep Space Nine's Bajoran wormhole stays conveniently open for business, guarded by godlike aliens who apparently double as interstellar civil engineers. Why does pop culture cling to these twisted tunnels? Beyond their narrative convenience, wormholes tap into something primal, the dream of breaking free from limits. They're the ultimate metaphor for escapism, curiosity, and the longing to rewrite our destinies. When Event Horizon turns a wormhole into a hellgate bleeding nightmares, or Contact's tunnel becomes a celestial cathedral, we're seeing science fiction grapple with the same awe that grips physicists staring at their equations. The difference: Hollywood trades uncertainty for spectacle, replacing Hawking radiation with rainbow vortexes, and quantum foam with hissing portals rimmed with convenient plot exposition. Yet these stories do more than entertain. They shape how we imagine real scientific breakthroughs. The Stargate effect, matter digitized for transit, inspired real proposals for quantum teleportation. Interstellar's black hole visuals led to genuine astrophysics papers about gravitational lensing. Even when sci-fi flagrantly cheats, it plants seeds in young minds that blossom into careers. Every physicist who chuckled at Thor's Einstein-Rosen bridge explanation still secretly loves that the Marvelverse name dropped real theory. Because in the end, pop culture's greatest wormhole trick isn't bending space, it's bridging the gap between equations and wonder, making the cosmos feel thrillingly close, even when the science says not yet. From the cold equations of relativity to the fever dream frontiers of quantum foam, wormholes have taken us on a journey through physics' most dazzling possibilities. We've seen them as cosmic subways forged by collapsing stars, as quantum threads stitching together entangled particles, even as hypothetical time machines twisting causality into knots. Some theories ground wormholes in razor-sharp math: Einstein's bridges, Morris Thorne tunnels, holographic entanglement. Others catapult us into the speculative wilds, civilizations riding dark energy highways, neurons whispering through Planck-scale shortcuts, entire universes dangling like dewdrops on a multidimensional spiderweb. What unites these visions isn't proof, it's audacity. Wormholes remain firmly in the realm of could be, their existence hovering just beyond our telescopes and colliders. Yet their power lies precisely in that uncertainty. They force us to confront spacetime not as a static stage, but as a living, twisting entity that might hide doors in its folds. Every unproven wormhole theory is a crack in the ceiling of conventional physics, letting in light from stranger, grander possibilities. The real magic happens in the questions they leave dangling. Are we alone in the universe, or is some advanced species already threading galaxies with wormhole networks? Does consciousness tap into hidden space-time tunnels we can't yet measure? Could the universe's darkest mysteries, dark matter, quantum gravity, even the arrow of time, be clues to a cosmos webbed with invisible shortcuts? For now, these remain dreams scribbled in the margins of textbooks. But history tells us today's wild speculations often become tomorrow's breakthroughs. Black holes were once considered mathematical oddities before we heard their collisions echo across the cosmos. Quantum entanglement seemed like magic until it powered unhackable encryption. Wormholes might follow the same path, from heresy to hypothesis to reality. So here's your invitation to the cosmic debate. Which theory electrified your imagination? The holographic wormholes encoding reality's blueprints, the neutron stars hiding tunnels in their quantum hearts, or the spine-tingling idea that our universe's expansion might be fueled by countless invisible throats breathing in the void. Drop your favorite in the comments, and if you've made it this far, you're clearly the kind of explorer who thrives where physics meets fantasy. Hit subscribe because this journey's far from over. The universe's greatest mysteries don't knock twice, but we'll keep listening for them.